One of the cool things about being able to write complex numbers in trig form is we can now find square roots, cube roots, fourth roots of complex numbers that are not real, which is something we could not do in algebra. So let's take a peek at finding some roots that we already know how to find using algebra, but to find out something special about the relationship of those roots. Okay, so you're going to be asked to find the square roots of a given complex number. So if I want to find the square roots of 1, I'm trying to figure out what are the numbers that when I square them, I get 1. Which is the same thing as solving this algebraic equation. X squared minus 1 equals 0. We know how to solve that algebraically. X squared is 1. So we apply our square root property. So we say then that x is the square root of 1. And we know that there are two numbers that we square to get 1. So we know it is plus or minus 1. So we take both roots. Okay? So 1 is a square root of 1, and negative 1 is a square root of 1, because if we square those, we get 1. So this quadratic equation of degree 2 has two solutions, okay, which means 1 has two roots, okay? So we have two roots, or two square roots of 1. And they are, we use the letter Z to represent complex numbers. So we can say one of our complex roots is 1, and our other one is negative 1. If I graph those complex numbers in the complex plane, I've got 1 is here, and negative 1 is here, both on the real axis. Okay, so I have two roots. Now, look at the spacing of those roots about a circle here of radius 1. To get from one root to the other, I simply add, or basically they're 180 degrees apart. Okay, so they're evenly spaced 180 degrees about a circle of radius 1. So we say that if we're trying to find square roots of any complex number, there will be two of them, and they are spaced 180 degrees apart, which is basically 360 divided by 2. Okay? All right, so we don't really need trig for that, but we could do it using trig form of 1 if we wanted to. Okay, let's look at finding the square roots of negative 1. What are the numbers that you square to get negative 1? So it's like solving the equation x squared plus 1 equals 0. So x squared is negative 1. So we know x is the square root of negative 1. Okay? So this is why we're saying we're looking for the square roots of negative 1. Well, we know from algebra that we want both of those roots. So we want the plus or minus, and the square root of negative 1 is I. So I have, once again, two roots, two complex numbers that are roots that when I square them, I get negative 1. One of them is I, and the other one is negative 1I. Okay? If I graph those in the complex plane, then we can see then they are both located on the imaginary axis. So this is I and this is negative I. And once again, spaced evenly about a circle of radius 1, 180 degrees apart. Okay? Now, just to double check, let's think about what we know about I. We know that I is the square root of negative 1. We know then that I squared is just negative 1. So I can check to show that I and negative I are, when I square them, I get 1. Okay, so if we do a quick check, if I take I and I square it, I get I squared, which is negative 1. If I take negative 1i and square it, I get I squared again, which is negative 1. So both of those complex numbers, if I square them, I get negative 1. Okay, so let's move on and let's look at fourth roots now. Okay, so I'm sure you can guess now, if we're talking about the fourth roots of 1, that there should be 4 of them. Okay, whoops, a little crazy there. Yeah. Anyway, all right, so it's like solving this equation. X to the fourth equals 1, which means x is the fourth root of 1. So what are the fourth roots of 1? Okay, well, we probably already know that 1 and negative 1 are roots. We can find them algebraically. Okay, so I could set that by solving that polynomial equation. I can solve it by factoring, difference of squares. And then I could set each of those factors equal to 0, and I have 4 solutions, or I have 4 roots. They are I, negative I, 1, and negative 1. Oops. 1. Okay, so there are 4 roots. If I graph those in the complex plane, then I've got 4 of them, 2 on the real axis, 2 on the imaginary axis. So they're evenly spaced about a circle of radius 1. Okay, so what is the distance between them? They're evenly spaced how many degrees apart? 90 degrees apart. So if I'm talking about the fourth roots, there will be 4 roots spaced. We can always just take the full circle rotation, 360 divided by 4 will be spaced 90 degrees apart. Okay. All right, how about cube roots? What if I want the cube roots of 1? Okay, we see the same kind of situation, solving the equation x cubed equals 1. So x is the cube root of 1. Okay. I know this is a degree 3 equation, so we know that there are 3 solutions or 3 roots. Okay, now let's look at this graphically real quick. If I graph this function, y equals x cubed minus 1, okay, it's our basic cube root shifted down 1. So remember, our solutions or to this equation are the zeros of this function, okay, or the x-intercepts if they're real numbers. So I've got 1, 0, or 1 real solution, because it's an x-intercept, so it is the point 1, 0. So that's a real solution to this equation. So I know one of them. I know x has to be 1. But there should be 3 solutions. Because this graph only has 1 x-intercept, it only has 1 real solution. So that means my other roots are non-real numbers or imaginary numbers, which we can't find by just taking the cube root. We can't find all of them. So if we set this equation equal to 0 and solve by factoring, we factor it as a difference of cubes, okay? And this binomial factor in here is not factorable. So when I set this factor equal to 0 and solve, I have to use quadratic formula or completing the square, or I guess those are probably my only 2 choices there, okay? Which means I'm going to get 2 non-real solutions, okay? Now, Now, we could do that, but that's algebra. Let's transfer this over to trigonometry, okay? And let's talk about what we know or we have seen so far. If I have one root, I know one of these cube roots. I know my first root is 1. I know that 1 cubed gives me 1, okay? So let's graph this, and we've got right here. Here's my first root, okay? Now, we know because it's cube roots, we are going to have 3 roots spaced evenly about a circle of radius 1. They're going to be 360 divided by 3. They're going to be spaced 120 degrees apart. Okay? So my next root is going to be on the circle on the terminal side of an angle that is 120 degrees from my horizontal axis. So if I go 120 degrees, then I am approximately here. Okay? So here is the location of my second root. Okay? So this is z sub 1. This will be z sub 2. Okay? So what is that complex number? Okay? Well, we know, remember, that this distance that complex number is from the origin is r, or is 1. So we've got our complex number z sub 2. We can write it in trig form. So that complex number is 1 unit from the origin. And then I can say, okay, CIS, cosine I, sine, and its direction angle is 120 degrees. Which I can then turn that into rectangular form or standard form so that I can see it in a plus bi form, and it looks like a complex number that we're used to. Okay, so that becomes what? 1 times the cosine of 120, which is negative 1/2, plus the sine of 120, which is square root of 3 over 2 times I. So we end up with negative 1/2 plus square root of 3 over 2i, which is exactly one of the solutions you would have gotten up here to this equation if you would have solved using the quadratic formula. Whoops, totally missed that. Okay, so ultimately, if this is a circle of radius 1, this is a unit circle. So the A and the B, this is my A and this is my B, are the coordinates of that point on my unit circle. So here is my second root. Okay, and then how do I find my third root? Well, then I add 120 degrees to that. So 120 plus 120 is 240. So my next root is down here at 240 degrees. So it's the A and B for that will be the coordinates of that point on the unit circle at 240 degrees. So my third is 1 unit from the origin, its absolute value or modulus. CIS, how did I get that? Well, I added 120 degrees to the previous root. Okay, which this comes out to be 1 times, once again, negative 1/2, but it is, whoops, bad habit, minus square root of 3 over 2. So cosine of 240, sine of 240, which I end up with negative 1/2 minus square root of 3 over 2i. Okay, so here are my 3 roots, which means if I take each of these 3 complex numbers and cube them, I will get 1. Okay, so you could cube them the old-fashioned way over here in a plus bi form, or you could use the trig form and cube them using de Moivre's theorem. So if you're going to check, that's up to you which way you do that. I would think if it's big numbers, big roots, I would definitely use de Moivre's. So I have my 3 roots. Okay? So that's the procedure that we use to find the roots of a complex number using the trig form, that same procedure. So let's go through an example and do the official steps. Okay? If you have your guided notes, this is where we're following along. Okay? Steps for finding roots of a complex number. Okay? Every complex number has n different nth roots, means there's a certain number of roots that you can raise to that power. They are all different. So, for example, I want the 4th roots of 16i, which means I want to take the 4th root of 16i. Okay? So what we do is, because 16i is a complex number, it's a non-real number, which we can't take roots of non-real numbers algebraically. Okay? We're going to write 16i in trig form and then raise it to the 1/4 power. So knowing that the 4th root, remember, is a 1/4 power. Okay, so first step, I'm going to decide how many roots do I have and how are they spaced about the circle. Well, if it's 4th roots, there are 4 of them. 360 divided by 4 would be, they're spaced 90 degrees apart. So if you were looking for the 7th roots, you'd take 360 divided by 7, and whatever that degree measure is, you would space them that distance apart. Okay, so here's where trig form comes in handy. Convert the complex number to trig form, which we've done a lot of. So 16i is located in the complex plane on the imaginary axis. Okay, so it's up here, 16i is up here. All right, so remember we need r, which is the distance, and we need theta, which is the direction angle. Okay, so 16i can be written in trig form. Let's use compact form because it's so much nicer. R is 16. It's 16 units up on the imaginary axis. So R is 16, CIS, theta here is 90 degrees. Okay. So what I'm going to do is I'm going to find my first root using de Moivre's theorem by raising 16i to the 1/4 power. But I can't do that in that form, but I can if I use trig form. So 16i in trig form is 16 CIS 90. Okay, and I'm going to raise that to the 1/4 power. De Moivre's theorem, remember, tells us how to raise a complex number in trig form to a power. And if you recall, we do the r, or the distance, to the 1/4 power, and we take the angle and we multiply by 1/4. Okay? And that is going to be our first root. So 16 to the 1/4 power, which means the 4th root of 16, which is 2. So all of my roots are going to be 2 units from the origin. They're all going to have an absolute value of 2. 90 divided by 4 is, 22 degrees. So I have 2 CIS 22, 0.5 degrees. Okay, so that's the location of my first root. So I can say then that, I'm just going to come down here. Z sub 1 is 2 CIS 22.5 degrees. Okay, so you're going to be asked to find the complex roots and then graph them. They say as a vector located in the complex plane. We aren't studying vectors, but basically a vector has an end point, extends indefinitely in one direction. Okay, so this is saying we have our circle. What's the radius of our circle? It is 2. Okay, because the distance from the origin to that complex number is 2. Okay, and this complex number has a direction angle of 22.5 degrees. Okay, so if I want to find my next root, then I know they are evenly spaced about the circle. So from my first root, I add 90 degrees because they're evenly spaced 90 degrees apart. And I've got the direction angle of my second complex number, or if we were talking about the vector associated with it. Okay, so I end up with 2 CIS 22.5 plus 90 is 112.5 degrees. Okay, so we know 90 is a right angle, so the other one's going to be over here somewhere. Not drawn to scale, by the way. Okay, so here is my second root. Okay, so this is 90 degrees. And then I just continue to find the remaining roots by adding 90. They're going to be 90 degrees apart. Okay. All right, so if I add 90 and then do that another time, I will have all of the roots. So my third will be 2. Once again, 2 units from the origin. CIS 202.5. And the fourth root will be 2 CIS 292.5. Okay, those are in trig form, which typically, when the angle is not a nice unit circle angle, then we don't turn them into, or write them in rectangular form, a plus bi. If we did, we'd have to use a decimal. So we usually just stop there unless we need that equivalent. Okay. All right. One more quick example. Let's do the square roots. Find the square roots of negative square root of 3 minus I. That is equivalent to asking you to find solutions to this equation. Okay, so you could see it in different forms. So if I isolate my x squared, I have negative square root of 3 minus I. I just add that complex number. And here's what I'm trying to find. My solutions to this equation will be the square roots of negative square root of 3 minus I. Okay, which means I am trying to find negative square root of 3 minus I to the 1/4 square roots should be 1/2 power. Okay, so we know there are going to be 2 roots spaced 180 degrees apart about my circle. Okay, so first thing we're going to do then is write that complex number in trig form, which we have done, so I'm just going to go ahead and go to that. So if I have negative square root of 3 minus I, remember this is located in quadrant 3, and it's going to be also 2 units from the origin. So I have 2 CIS 210 would be its equivalent. Okay. I'm going to find the first root. So I'm going to take the 2 CIS 210, and which is the equivalent for the standard form, to the 1/2 power. Okay. So we take the R value to the 1/2 power, and then according to de Moivre's, we multiply the angle by the power. Multiplying by 1/2 is dividing by 2. So this becomes the square root of 2, which we'll use the exact value, CIS 110 degrees. Whoops, how about 105 degrees? Close. 105. Okay. All right, so that is my first root. Okay, so that's Z sub 1. Complex number that's square root of 2 units from the origin on a direction angle of 105 degrees. Okay, so my circle is of radius square root of 2. 105 degrees is located in quadrant 2, so up here somewhere. Okay, there's my first root. If we associate it with a vector, you'd see this segment here going from the origin, or that ray, I'm sorry. Okay, and I know then that this is 105 degrees. So that's the location of the first root, is always the measure from the positive horizontal axis. So to get my next root, they're spaced 180 degrees apart, so I basically just add 180 to that. So my second one is still on a circle of radius square root of 2. It's on a direction angle or terminal side of an angle of, what is that, 295? Okay, which would be 180 degrees from there. So it would be directly across here. And that would be my second root. So this distance between roots is 180 degrees. So the angle of your first root is where it gives you your first solution, and then you can just add the spacing from there.